substrate. We have given an electron to the substrate. This was the first case where we actually did the other way around. We oxidized the substrate. And so this is only a few slides. This is what I would like to show you simply as the alternative. Instead of doing a single electron reduction, we can also do single electron oxidations. And I will show you just a few things which are easy to do. Oxidations of amines, that is typically very easily to be done because these N-centered radicals, especially if it is in conjugation with a carbonyl group, this is a relatively stable radical. And so again, it was shown that this idea of doing a proton-coupled electron transfer is also a very good way. But now it goes the other way around. Before this, we used the proton to stabilize an anionic charge. Now we're actually abstracting the proton to get an anion because the anion is easier to be oxidized, right? So it's the other way around. And again, this was shown very nicely in the publication here, that if you have these amides, that in the presence of a phosphate base, that single electron oxidation to form the N radical, and presumably you can think about this by deprotonating, then you have the negative charge here, and then oxidizing this, that you can form the N-centered radical much easier. And then this N-centered radical, in this case, again, it is doing a 5-exo trig cyclization. That's always very favorable. And in this case, I think I should have put in a third acceptor molecule. They were actually trapping then the resulting radical with another alkene in order to do this. But this is, again, the more important thing is again the oxidation, and the oxidation is generally helped by going through the carb anion rather than through the neutral species. Okay, and here's another example which I think really, and that came out in the early stages of the modern photochemistry, came out by David Nischewitz, and I think this is also very spectacular because it showed that you can do anti-Markovnikov reactions, additions to alkenes. And we all know Markovnikov, adding water to an alkene easy, right? Protonation, more stable cation, and then this will give us the product. So for example, if we have any type of styrene, and if we would add acid catalyzed water to it, then this would be going through the more stable cation, and then the water would give us this alcohol, this water addition. How would we normally get the anti-Markovnikov? How would we normally get the anti-Markovnikov way? What is the alternative if you want to go to here? And that's also very, very important, and especially it's important in industry when they want to take alkenes, add water to make the terminal alcohols, and then if you oxidize the terminal alcohols to aldehydes or carboxylic acids, these are very useful ways. How do we normally do this? Should have put up that as a Slido question, but I forgot. What's the reaction we use? Sorry? No, we are not using the oxymercuration, because the oxymercuration gives us what? The oxymercuration gives us still the Markovnikov products, right? You have mercury acetate, and you go through a intermediate of this type, and then it will open up, water will attack on the higher substituted carbon, because that's more stable, right? It's an SN2 reaction, it's more stable, and then you go through a intermediate which looks like this, mercury acetate, and this usually you need to reduce with sodium borohydride in order to get this. But this gives you the Markovnikov adducts. That is the typical method you would use in a laboratory, because if you do what industry is doing, acid, water, that needs high temperature, gas phase chemistry. That's not a good laboratory method. But that is still Markovnikov. How do we do anti-Markovnikov? A Nobel Prize was awarded for that reaction. I give this to you as a hint. Sorry? Hydroboration. Exactly. Hydroboration is the chemistry, right? So who got the Nobel Prize? Does anyone know? Herbert Charles Brown. At least in Germany, we can remember that name so easily because the Peanuts, that comic, right? Charlie Brown, same name, right? So Herbert Charles Brown, and what did they do? Boron. You heard already today a lot about boron chemistry, boron NMR, and then work up with hydrogen peroxide. It's a great reaction. It got in 1977 the Nobel Prize together with Georg Wittig. So Wittig got it for the olefinations, Brown got it for the hydroboration chemistry. It's of course fantastic, but the problem is boron stoichiometric. On the other hand, do we have a lot of boron? How abundant is boron? Is that okay? It's very okay. It's one of the most abundant elements you have on Earth. Aluminum is maybe more, it's the same group, it might be more, but boron we have a lot. But what is the problem? If you want to do hydroboration, large scale, how do you get BH3? So I was there when you heard about the boron NMR today. There was a lot of talk about BH3, but how do you get it? And it was said you can buy it, but how do you make it? It's not natural on Earth, not BH3. What is our boron source? Sorry? Sodium borohydride. No! Think about this. It would rain one day and then all the sodium borohydride would be gone, right? No way. No, it's boron oxide, B2O3 or so, these minerals, bauxite. So it's the oxide of boron, and in order to make borane, you need to reduce it. And this is very, very, very energy intensive. So we come again back to this old question, if we have abundant energy from green resources or so, we would not have to discuss many issues, but we don't, and that is the problem. This is the problem, it's very energy intensive. Same with aluminum. We want to recycle our aluminum cans for a good reason, because first of all, I think we should like recycling. But the reason behind this is we have enough aluminum, but we have it as in its oxide form. And to make metal aluminum, it's one of the most energy intensive processes. And in fact, I give you an idea, I have a former PhD student who works at a company in Germany who make aluminum by these electrochemical electrolysis thing. And especially when we had the energy crisis or so, and Germany tries to do a lot with renewables. And one of the things with solar and wind is you cannot regulate it. You cannot say the sun, please now on, and so on. And so what happens is that the German government takes these companies who make aluminum, for example, and has agreed with them that if we don't produce enough energy through the renewables, that they can shut down their aluminum plant. They take away their electricity, so then they don't have electricity. You can only do this so much because you also need high energy because you melt the aluminum salts, but you can take away a little or quite a bit of the energy. You cannot get it down to room temperature. You still have to keep it up. And then on the other hand, when the sun is shining and the wind is blowing and we overproduce, that's also what we do in Germany, then the industry gets it essentially for free. And so that is my former coworker said, it's an okay deal. We have it, and sometimes that we have to shut down the production, and then 2 hours later they switch everything back on, but they have lived with this, and in a way it can save them money, right? So again, so it's very energy intensive, great reaction, not really from a scarce source, but nevertheless it is it has this energy problem. And so David Nischewitz showed how you can do these type of anti-Markovnikov chemistry in a photochemical way. And the catalyst he's using is the so-called Fukuzumi catalyst. Fukuzumi, a Japanese scientist who pioneered this and also already showed how to do photochemistry with this. These are these acridinium salts. And you can probably immediately understand that this should be a good catalyst for oxidation, right? Because it's positive. Whenever something is positive, it wants to have an electron. And so that is also what these acridinium salts want. And then you see there are a lot of arenes around there, so they absorb in the visible light region. And so this is a fantastic catalyst for oxidation. And now it does exactly the opposite thing, what we discussed just a little bit earlier about the reduction of the alkene. So with the Fukuzumi catalyst, let's say we have a styrene, it can take away an electron. And so if it takes away the electron, we have the same situation. We can draw either this structure, or we can draw the resonance structure in the other way. And we have already discussed if now a nucleophile is coming, like water, it will want to attack this structure, because then we are getting the more stabilized radical. And if this can abstract a hydrogen, and you see Nischewitz, he is using thiophenol, and so the thiophenol can deliver a hydrogen because it's a very good hydrogen donor and it can make this thioradical. How do we get now the catalyst back, right? We have reduced the catalyst, so now we need somehow to oxidize the catalyst. How do we do this? Who is helping us, or who is doing the oxidation of the catalyst? The sulfur radical, exactly. Right? Very easy to be reduced. So this takes one electron from the reduced photocatalyst, right? So this makes plus one electron, and then it's the catalyst, which is essentially in the reduced form, and then it can reduce the thioradical. So that is what is being indeed used quite a bit. So that technology works very nicely. Hydrogen donors, thiophenols are fantastic. What's the downside on the thiophenol? They stink, right? You can say this. They are not very good. And so typically what people do instead is they're using the disulfides, because under light irradiation they can in situ then do the homolysis and form these thioradicals. And then very often nowadays people also use some substituents here to make it less volatile, right? Because usually when we use the thiophenol, or whoever uses thiophenol, the whole department at least knows, right? Sometimes you have the feeling the whole university knows. So it's pretty bad. So yeah, so that is, and I think again, that is a spectacular way to show that photocatalysis can do something you cannot easily do otherwise, right? Very often we have reactions which we can do otherwise, but they are might not be just as convenient, but in this case, it is actually the difference. And the Michaelis groups also very importantly showed that you can do fluorination with this, right? And so they are using this complex of HF is triethylamine. That's a very convenient way to use HF. HF alone is not very good. You cannot use glassware and anything, but these triethylamine HF complexes are good to use, and there, instead of having the hydroxide as a nucleophile, he was able to show that you can use the fluoride as a nucleophile, and you can see here they are able to do fluorinations also very nicely. Why are fluorinations so important? Why are we so interested in fluorinations typically? Yeah, why is pharmaceutical industry interested in that? What is the fluorine doing? You're absolutely right. It's a pharmaceutical sector who wants it. Fluorine has more or less the same van der Waals radius like hydrogen. So if you put in a fluorine atom, you do not change the sterics dramatically. Changes a little bit, but by and large, a fluorinated drug will in the same way interact with the receptor like a non-fluorinated drug. But the fluorinated drug is more polar. And that typically means you get it faster out of the body again. And one of the big problems is when you have, for example, chemotherapy, is that you want to kill the cell, but then once this job is more or less done or so, you want to flush out the system. And fluorine is helping to do this. And so a very common strategy in pharmaceutical industry is you first develop the drug, but then if you have a drug, you see if you can improve on the pharmacokinetics by putting fluorine in various positions, right? And that it's very many cancer drugs we have are fluorinated. Also, many of the HIV drugs have fluorine atoms in there. And again, it has nothing to do with the activity. It has something to do with getting it out of your system. Okay, so and that's a very good way to get fluorine also in this. Here's again the mechanism. We have just talked about this, the acridinium cation complex. If that takes up a radical, you see it makes a highly stabilized radical, so that is very, very good to do. But then in the end, if the thiol has given the hydrogen, the thiol radical then can reoxidize the reduced Fukuzumi catalyst and become the thiolate, which can pick up a proton. I think this is extremely nice and very, very good chemistry. There are a few other radicals which you can generate quite easily by oxidation, and so this is actually something we did early on in the chemistry, that we realized that you can oxidize nitrogen very, very easily. And so in this case, we are using an iridium catalyst, and so all what is done here is in the first step, maybe I give us a new page here. So typically amines are very easily oxidized, and especially if you have such an N-phenylamine, because then essentially you go through a benzylic radical. So you go through this. Now typically, if you have a radical cation like this, what happens to the proton which is next to that radical cation? Something happens very dramatically. It becomes very, very acidic. It is suddenly a very strong acid, much stronger than without this. So if you would like, in the ground state, if you would like to deprotonate this, you would need a strong base, LDA or something like this. This probably has a pKa of around 30. If you oxidize the nitrogen to the radical cation, it goes by itself. I'm not really sure where it is, pKa of 5 or something like this. Because the reason for this is that the N radical cation would like to get rid of the positive charge. It's always the same with organic compounds. They don't like charges. And in order to get rid of this, in order to get rid of the positive charge, is that in the easiest way, you will simply deprotonate this, and then now you have this, and I can rewrite this by giving one electron from that negative charge to the nitrogen. Then the nitrogen has the normal pair again. And then I have a radical here. So this is a very good way to make so-called alpha amino radicals. Very easy to obtain by oxidation of an amine, and you need in the neighborhood, on the next carbon, you need a proton. And these radicals are very stable to the point that they might be almost persistent radicals. Because again, they benefit from the lone pair of the nitrogen. And in addition, the specific case we have here, it's a benzylic radical as well. And so this can be very easily generated. And this way we are able to, again, it's a nucleophilic radical. So again, these are nucleophilic. And I think it's also clear why this is, because it is because it has this donor in the neighborhood, and so consequently it reacts very well with electron deficient substrates in order to do the type of addition. Okay. I'm not sure. We are running a little bit out of time. In the tutorial, I will discuss some stereoselectivity with you, but we can keep this for the tutorial without that I explain this. We introduce it then, something which is called de-racemization. So allow me, for the remaining maybe 30 minutes, where do I find it? The next lecture? See, this is terrible with me. I'm a Mac person. When it comes to PC, I have no idea what to do with these. I could have done this, but I didn't know how. Yes. So now allow me a 30-minute commercial break. Because the commercial break is that I will show you a little bit what we do in photocatalysis, and I hope it will contribute and give you some feeling what are the chances and also what are the difficulties when you want to use earth-abundant photocatalysts. And so let me show this to you. So again, this is you have seen this picture already. You have seen the picture of my group. And I could ask you, what is the biggest challenge to use 3D metal catalysts as photocatalysts? Because we have seen a lot with ruthenium and iridium, right? And so why not simply saying, why should I use an expensive metal if I can use with iron or copper, right, or some other things? Why is that not so? Why is that not so simply done? Again, new number here. It's a little bit better now with the temperature, right? I think. Very good. Okay, now we're getting some answers here. Very good. Thank you for participating. So if you start with this, cost of the complexes might depend. First of all, copper, iron is 1 million times cheaper than iridium and ruthenium. So there we are on a pretty good page. And then, of course, you're absolutely right. In a way, absolutely right. The ligands might be different, but the ligands might be in cost also different than for ruthenium and iridium. So overall, simply the metal is much more abundant and it's much, much cheaper. The dynamic ligand exchange, that's an interesting issue with solvent or substrates. That is indeed why people said 15 years ago 3D metal complexes are not good. Because the ruthenium and iridium complexes, we didn't talk about this, but there the pyridine and the ligands they have, they stick on there and they are not exchanging. They are not really dynamic. But copper and iron, they do this. They get exchanged like acetonitrile. They start exchanging the ligands for acetonitrile. Acetonitrile itself is a pretty good ligand, right? Ruthenium is not really impressed by ruthenium BP complex. It's not really impressed by acetonitrile as a co-ligand. But copper thinks is why not? Why not exchanging a ligand? And this is of course immediately a problem because you might not have a defined photochemical photoactive species. And so that's why people said, well, maybe that's not good. On the other hand, you could think about this if it is dynamic, even if you don't have all the time, the ligand you need, of course, for the light absorption, even if you don't have it all the time, you might have it some of the time, which might be important or sufficient. And the other thing, I showed you already this spectacular example of this chiral copper photocatalyst from the Emerging group from 2024. The advantage might be that if it is dynamic, it might interact with the substrates. And so that is something which is indeed the case, and that is something which we also like. Insufficient light absorption, nobody said this. You will see that some of the copper complexes are not really having high absorption maxima, but absolutely sufficient for photochemistry. So that's okay. So again, if you look at this, ruthenium and iridium, this was by far, at least also 10, 15 years ago, by far the complexes people would use most. Oh, but I should go back. Did we have this? Dynamic short excited state lifetimes. Okay, I say something here on this in a moment. So ruthenium and iridium quite a bit. Eosine dyes were also used quite a bit. And I've shown you a few examples of this already. Nowadays, these 4-CCIPN, these polyaromatic compounds which have these carbazols ligands around this, they're also very popular and they're also very good. The interesting thing is, from the price, if you buy it from Aldrich or so, we make it, the price is always as high as iridium. And so they are really expensive, and the reason is they are not so easy to make. One of the biggest problems with iron and copper and 3D metals might be that they have much lower excited state lifetimes than iridium and ruthenium. Iridium and ruthenium is already in the microsecond range. The earth-abundant metal complexes are typically in the nanoseconds. With iron, most of the time they're even lower, picoseconds. I think this complex I show you here is the world record, 2.4 nanoseconds. That's 1,000 times less than the ruthenium Bipi. Okay, so that is the problem, that intermolecular reactions might not work. When we started, we were aware of work from physical chemistry which characterized copper phenanthroline complexes. And there we felt the excited state lifetimes, some of them all the way up to 300 nanoseconds, that might be okay. And now it also becomes very clear that such heteroleptic complexes, which have one phenanthroline and one phosphine ligand coordinated to it, they have even longer excited state lifetimes, rivaling the iridium complexes. However, they rapidly exchange the ligands, and that can be a disadvantage, but this can also be a big advantage. And I'm not sure I will be able to come to this today in order to discuss this with you. So this was pretty much the starting point. And so this is how we started. We felt this is a complex which was known in the literature. This is a copper complex, copper 1 complex, which has these very bulky phenanthroline ligands. You see it's a phenanthroline, and then it has the two para-anisole ligands on this as well. So that's sterically very, very bulky. And it was known, that complex was known. And the reason that was known is that Jean-Pierre Sauvage, who got the Nobel Prize, I forgot the date, but it was some time ago, he got the Nobel Prize for making catenans. And catenans are these compounds where you make two rings which grab in each other, and then they cannot escape, although there's no bond in there. And the way Sauvage made this is that he used copper complexes as a template. So he made a tetrahedral complex which has ligands on there. And so the copper would bring them together in a tetrahedral way, and then he had a reaction which would clip the ligands at the end together. And then he removed the copper, and that's how he got these type of compounds. And so Sauvage made these copper phenanthroline complexes, especially the one with this ligand, and he did everything already. He did the characterization, so the UV spectrum was known, 450 nanometers, and it was also the excited state lifetime was also known, 270 nanoseconds. And when we started the chemistry, we thought maybe that's sufficient. And then at the same time, it is also pretty much clear why these excited state lifetimes are so short. Because if you do an electron transfer on the first phase, you go from copper 1 and you give one of the electrons to the ligand, so to make a metal to ligand charge transfer, you go from copper 1 to copper 2. And copper 2 wants to be not tetrahedral any longer, it wants to be square planar. And this motion deactivates the excited state. Right? It wants to planarize, and that's the problem why these, and that's the case with all these 3D metal complexes. They are too mobile, and therefore quenching the excited states through these vibrations. And there's another thing which we found out, that if you go from copper 1 with this very bulky ligand, if you go to copper 2, so you do the electron transfer, look at this. This is the X-ray structure of the copper 2 complex. It loses the ligand. And that's probably also clear why that is, because these ligands are very, very big. And so if I be copper 1, tetrahedral, I'm okay. But if I go copper 2, then you see, they start clashing if I planarize it. So one ligand goes away. And then again, it's the question, is this an advantage or it's a disadvantage? And we think it is an advantage because now small substrates can interact. And that's what we also saw already in the example of Wenjing Zhao, that he would able to trap radicals with copper 2. And so this is more or less how that started for us. With the copper 1 complexes, you go in the copper 1 excited state, and there you can do a reduction. You can reduce halides, for example, and it has a reduction potential, which is actually, it's a stronger reductant in the excited state than ruthenium Bipi is. You bring it to copper 2, and then it becomes a very it is a very weak oxidant. To bring it back to copper 1 from copper 2 to copper 1, the oxidation potential is really low, and that is different. And this can, you will see, it can have an advantage, but can also be a disadvantage. So this is the typical chemistry you can get out of copper 1. From copper 2, we are using a different type of activation principle. And what we do here is we are coordinating a substrate to the copper 2, and then upon light irradiation, if that cleaves homolytically the copper substrate bond, we form a radical and we have the reduced catalyst, right? So here we oxidize the catalyst, but here when we start from copper 2, we are reducing the catalyst. And both of these modes are very valid if you do photocatalysis with copper. We see nevertheless that many of the reactions which are done, we see many papers come out and they have not screened copper, and we are not particularly offended about this, but sometimes we wonder why didn't they try copper. One of the reasons could be is that this ligand, this anisole ligand, you have to synthesize, and in order to cells this whole copper complex for, I think, 1,000 euros. That's what? That's 100,000 rupees per gram. Anybody who wants to buy it from me for 1/10 of the price, please let me know. Because we all know that with Aldrich, everything is at least 10 times, probably 50 times more expensive. And so in the literature I read a lot is that they say, oh, but your copper complex is so expensive. We have in one of our papers, we have a procedure how to make it, and it's not really hard to make. The other thing is this ruthenium bipi has been commercial for a long time because people use it for luminescence, and also some of these iridium complexes, because they go into the lamps, are also commercial. So that's why they were so much less expensive, simply because they were made on larger quantities. And so we feel it's not really true. But if you want to include copper complexes in your screening program, the one thing I can recommend is, instead of using the phenanthroline with these very bulky ligands, which are these para-anisole ligands here, you can use the same type of phenanthroline, which just has these two methyl groups here. That's 2,9-dimethyl phenanthroline. It's called neocoprine, and this is not quite as good as this other ligand, and we compared, with all the reactions we have done in this paper, we compared the two complexes, and very often the more bulky ligand complex gives you a little bit better yields. The reactions might be faster, because also here the excited state lifetime of these copper complexes with the dimethyl is only 20 nanoseconds. So it's about a factor 10 lower. But just to screen it and to see if copper will give you the chemistry, I highly recommend this. And this ligand is dirt cheap. It costs 8 euros per gram. And what you can do is you simply mix copper 2 chloride with this phenanthroline, and you get out the copper complexes. You get out this complex which has two of the phenanthroline coordinated. One chlorine is still on there, one chloride in the outer phase. And you can use those for copper 2 as well as for copper 1, because if you irradiate this, it might throw out one of the chlorine ligands. I show this to you, and makes copper 1. So you can use it as precursor. It's stable. You can just store it in little vials, and so it's really good to use. So that would be my recommendation if you want to include a copper complex into your screening program. The reactions we like to do are these atom transfer radical additions. And that is a reaction where you add a suitable precursor from which we can generate the radical. You add this to an alkene, and you get such addition products. And then very often, if this is a leaving group, like a halide, if you do this in the presence of a base, you can actually get an elimination, and you can form these type of alkenes. And this would be the product of a Heck reaction, right? That's a Heck coupling, which we know from palladium, when we can use L and vinyl halides to do this type of coupling. And we thought that maybe if we do it by the photocatalysis way, we could develop a copper-1 variant of the Heck reaction, light-induced. And this would not only allow to transfer arrow and vinyl, which is known from palladium, but maybe we can also transfer alkyl and heteroatoms, and that is indeed the case, so might be relatively broad. This is a reaction which was not invented by us, by no means. That is the famous Karash reaction, which was already known since 1940, doing this in a thermal way. And there are two ways people thought about this in the literature, how this reaction can proceed. You have your precursor, and from this precursor you generate the radical, and this can be done by a radical initiator, AIBN, for example, or it can also be done by the photocatalyst. So your photocatalyst needs to be able to reduce the substrate, you extrude the leaving group, and you generate a radical. And now this radical can add to the alkene, and it forms a new radical. And at this point, you have two options. This radical could start a radical chain mechanism. It could abstract your X group here, form the product, regenerate the radical. But also, to close the catalytic cycle, we have oxidized our photocatalyst. We need to reduce it, right? And in order to reduce it, we would have to oxidize this radical, which we earlier discussed with the furane example. So we are forming a cation, and this cation now, if this recombines with our leaving group here, we are forming the product. So these are the two mechanisms which were discussed. But copper might have a third option, and that is the option which we have heard already before. So we do with the copper-1, we do the reduction of our substrate, we form the radical, and the radical can add to the alkene, form a new radical. This is exactly what we have been discussing here. But when we do the electron transfer, we convert copper-1 to copper-2. And copper-2 persistent radical, and the copper-2 now can very efficiently trap these radicals. And you might form such a copper-3 intermediate, which is doing a reductive elimination now to the product. The alternative is that this radical could abstract directly, and that's also very efficient, directly abstract the X group from the copper complex. So either it interacts with the metal, or it can interact with the ligand and form this. And this type of mechanism seems to be superior to the mechanisms where you would just have a photocatalyst which cannot interact with the substrate. And so we find that we can run many of these reactions with copper, which we could not do with ruthenium and iridium. And the reason for this is that these transient radicals which we are generating here can interact with the copper, can get stabilized through a copper-3 intermediate, or very rapidly transfer the X group into the product. And so this was the chemistry we did. Both of these mechanisms are valid. We tested this by using isocyanates, and we know that the copper-2 isocyanate complex coordinates copper onto the nitrogen. And then we found that if we have a radical here, this radical could either form the thiocyanate, or it could form the isocyanate compound. So the thiocyanate would be formed if this radical attacks the sulfur. The nitrogen compound we would propose would form if the radical attacks the copper and then is doing a reductive elimination. And we found that it depends on the electronic nature of the radical that both modes can go depending if it's an electron-rich radical, it will attack the electrophilic copper center and makes the NCS compounds. If it's an electron-deficient radical, it will interact with the sulfur and as a nucleophile and make the thiocyanate. Okay, so then we did this quite a bit, and this was chemistry where we started with, and at that time we were very happy that copper would do this type of chemistry at all, and we could add quite a number of halides, typically activated halides, to all kinds of alkenes here. And then we found also later on that certain substrates, iodides, for example, would only work with copper and they would not work with anything else. And the reason for this is, in this example here with the perfluoroalkyl iodides, the reason we believe that this is happening is that once you form the radical of the perfluoroalkyl iodide here, if this adds to the alkene, this is very electron deficient, right? That's perfluoro, it's very electron poor. So this makes this a very electron deficient radical. And probably in the photocatalysis cycle, you would need to oxidize it in order that it can combine with the iodide and form the product. And this is hard to oxidize because it has this electron deficient substituent on there. But on the other hand, the radical chain mechanism might also be hard because the radical is hard, the iodide is soft, so that's probably also mismatched. And in our opinion, we are trapping it with the copper iodide, and that then after a reductive elimination, we are forming these iodides, and that is something which is really allowing us to do this chemistry. And iodides have always been very good for us. I show another example, not just that I'm happy to present more examples here, but there was something very interesting we learned in this study. And so you see here also, we are able to add iodoform, and iodoform is being added across the double bond here, and it's the same thing. By copper, it adds the iodoform and makes these highly iodinated compounds. I didn't even in the beginning thought that they might be stable, right? We have an X-ray structure here, and see we have here 3 iodine atoms in the product, and of course they might lose hydrogen iodide or so very easily. And so we were very happy, and we indeed found that this reaction only works with copper. It does not work with any other catalyst at all. But there was something else we learned. And now look at this. We are irradiating with green light here. That's 530 nanometers. And the absorption maximum of this catalyst is 455. And so I also asked my coworkers, I said, why do you irradiate with green light? If with blue light, 455, it would absorb much better. And they said, yeah, we did it, but if we irradiated 455, it doesn't work. I said, well, what do you mean it doesn't work? They said, it doesn't work. We're getting 0% yield, and we're getting great yield when we irradiate it at 530. So, okay, we said, if that's the case, and they said, yeah, that's the case, and they said, we write it into the paper. And so we wrote in the conclusion, and we would like further to point out that you have to irradiate at green light, you cannot irradiate at blue light, although, and we showed the UV spectrum, and clearly 455 should have been much better for the absorption. So one of the reviewers, very nice reviewer, came back to us and said, this does not make any sense. If the absorption maximum is better, he said, I can understand that it works at 530 because you're still absorbing in this region, but I cannot understand that you cannot irradiate at 455. And he was very nice. He said, you should take that sentence out. And I went to my coworker and said, you cannot take the sentence out. It's a fact. I went to my coworkers back and said, you guys are sure it works at 530, it doesn't work at 455? And they said, yes. I said, now you go back to your lab. It's 3 different labs. We have small labs, so I have lots of labs. I said, everybody runs this again and come back to me the next day and tell me about this. And they come back and say, it doesn't work at 455. And so we said, we cannot take it out then, but we need to find out why that is. And the reason for this, and I think that's a good lesson to learn, is we finally got the idea and said, well, maybe at 455, that's more energy intensive light, and maybe we start forming iodine. Very little, we couldn't see it, but the moment we added starch solution, that's the normal way to test for iodine, right? It turned blue. And so we knew that we were testing that. It was already known from work from Paolo Mercuri and also Corey Stevens, and that iodine can be a catalyst poison and quenches like crazy the chemistry. And so that is then what was going on, that we were building up iodine much more rapidly at 4:55 than we would do it at 5:30. And so that might be a good also, again, a good lesson that sometimes you need to, you might vary the light, and you might, normally you have the feeling that if it doesn't work at a one wavelength, if it works at the higher, the more energy wavelengths. But sometimes it's the other way around, because you might form a byproduct which might kill your reaction. And HI, for example, if that forms, it's also a very strong acid, right? As the strongest acid, more or less, we have. That kills also the copper catalyst. And so that was, so we added this explanation, and then the reviewer was happy, and so then we got it published. I think actually we noticed this, I think we had it actually in this paper, where we noticed this the first time. Okay. Here's another interesting thing which we learned, and which I would like to point out, is we looked at many of these reactions, and so we looked at sulfonyl chlorides adding to alkenes or adding to alkynes, and that again is a wonderful reaction. The reason for this is these sulfonyl chlorides are so easy to be reduced, and then you can add the sulfonyl chlorides on the double bonds or also on the triple bonds. And again, that works much better with copper than it works with iridium or ruthenium. Let me see if I have the mechanism. Again, we will propose that we are forming these sulfonyl radicals. And once we add the sulfonyl radicals to the alkene, we are forming this new radical here. And we believe that this radical, again, rapidly interacts with the copper-2 species, either delivering the chlorine from the outer sphere or adding to the copper, forming a copper-3 intermediate, which then makes the complex. And so that really works well. And it's one of the broadest ATRA reactions which we ever have reported, because it works with activated, unactivated alkenes, it works with alkynes, it essentially works with anything. And then it's an interesting substrate. Again, something I think one can learn. Very often you have these ATRA reactions or other reactions which might work with activated alkenes, but they don't work with unactivated alkenes. And then you have the possibility to say, oh, and our scope is limited to activated alkenes, and we cannot do unactivated alkenes. There's a better way to go about this. And this is, we have now routinely, using a substrate, let me see this, using routinely a substrate which looks like this. Look at this. This has an activated alkene, because activated means you have a substituent here which might stabilize the radical here. And then at the same time, this would be an unactivated alkene because it's not in conjugation to the phenyl ring. And very often, if you have a reaction which only works with an activated alkene and does not work with an unactivated alkene, you can use this substrate and do the reaction, and it will only work on the activated alkene. And this is also, by the way, true for the chlorosulfonylation. The chlorosulfonylation is faster on the activated than on the unactivated alkene. And so then in this case, rather than saying it doesn't work on unactivated alkenes, you can say, I have a chemoselective reaction because the activated alkene is preferentially functionalized and the unactivated alkene is left alone, right? And so we do this substrate, and we have the analogous substrate where we have an alkyne here, because sometimes, again, only activated alkenes work and the triple bonds do not work. And so you turn it into an advantage. Rather than saying it doesn't work, you say you have a selective reaction, right, by including both functionalities in one case. For the chlorosulfonylation, however, it works. It works in both cases. It works for the activated and also for the unactivated one. But interestingly enough, you need to add a base. And that is what we do a lot in photocatalysis. We add these inorganic bases and to make the reactions go better, right? And that is the case here for us. If we use the activated alkenes, we do not need any base. It works just fine. If we want to functionalize the unactivated alkene, we need to use the base. Well, it's not really clear to us Why do you think, what's the role of the base? And you have this in so many of these reactions, that you add bases, inorganic bases. They're not even really soluble in your solvent, in acetonitrile, and still reactions work very often much better. Is there a reason for this? Sagita, is this now the tea break time already? Oh, so last question here. Okay, we might include a few things with this hydrogen abstraction. Do we abstract any hydrogen in this reaction? We are adding a sulfonyl chloride on the double bond. There's no hydrogen abstraction. Right? That's okay. That's a very good point. Neutralization of acid. And I think indeed this is the reason what happens here. If the reaction is not completely efficient, you start making HCl. And the HCl kills the catalyst. If you have a very reactive alkene, it doesn't matter, because all the chloride goes into the product. If that reaction is not as efficient, you might do some unproductive chemistry. And think about this always. The catalyst is only there in 1 mole%. If you form 1 mole% of HCl, it might kill your catalyst. And that's I think the very important lesson, that the inorganic bases we have very often just take care of any type of acid which might form during the reaction. And almost all these metal complexes, and especially some of complexes like iridium PPY3, the iridium catalyst, they are extremely acid sensitive. And so that's why these type of scavengers help. Okay, then we do a coffee break, more or less short. And then I have to think about this, because my advertisement block could go for another 30 minutes here. And I hope also conceptually would be interesting. And I have also put up a few questions on the tutorial. So let's see how we continue. But let's first have a short coffee break. Okay? Is that the plan? Good. We all deserve it, right? You deserve it more than I do. But at least it's not cold here any longer, right? It definitely has done something here. Okay. So see you again in like 15 minutes.